Hello everyone, and welcome back. Today we're going to be continuing our exploration of elementary probability theory and discuss several different theorems and relations that are used when you have two or more variables that are potentially dependent on one another. In particular, we're going to be focusing on conditional probability and continued expectation, and we'll also briefly introduce some important theorems associated to conditional variance as well. So, a couple things that you definitely should know before diving into conditional expectation are the following two basic principles that you probably already know. The first is that the probability of A, assuming B has already occurred, can be represented as the probability of both A and B happening simultaneously divided by the probability of B. Some people will refer to this rule as Bayes' rule. And another very important principle that you definitely should know is that the probability of x can be represented as the sum from k is equal to 0 to infinity of the probability of a subscript k times the probability of x assuming a k has already occurred. And some people will refer to this property as the law of total probability. And if you haven't encountered the law of probability, it's actually pretty easy to understand. Practically what you have here is a sample space that's been partitioned into some subreasons, say A1, A2, A3, A4, and A5. And let's assume that you have some other event in this particular realm. Let's assume that we have this circle, and that's going to be region X. So the probability of x can be represented as a linear combination of the probabilities of these disjoint regions, which is x intersection with each of those a subscript k's. And by this Bayes rule, you can represent that product in terms of this conditional here. All right, so that's the law of probability and also Bayes rule. So now let's introduce conditional probability mass functions, and you can also define probability density functions, the conditional version, in a very similar fashion. So what exactly is a conditional probability mass function? So we define a conditional probability mass function as p subscript x given y of little x given little y, and this is going to be equal to, in terms of equivalent notation, some people will also use p xy of capital X taking little value x and capital Y taking little value of y. We're going to be using the former, and this is defined to be equal to the probability that x equals little x and y equals little y divided by the probability that y takes the value little y, right? So it looks practically like Bayes' rule, just a functional representation of it, okay? Keep in mind, x is usually the variable in this expression, and y is just a constant, all right? Now, we can represent this from the perspective of marginal and joint probability mass functions. So let's assume that p subscript x comma y is the joint probability mass function for x and y, both discrete random variables. And let's assume that p subscript y is the marginal probability mass function for y. Then if that is the case, we can represent this conditional probability, so the probability of x given y, of little x given little y, this is actually just going to be equal to the joint probability mass function x comma y, evaluated at little x, little y, divided by the probability that y takes the value of little y. And this is what a conditional probability mass function is. Okay, now one thing you should notice here is that we have the marginal probability mass function for y, the joint probability mass function for x and y, and the conditional probability mass function for x given a value of y. So if we notice, there is no joint or no marginal probability mass function for x. So this is not here. And let's assume that you want it, right? So instead of the conditional of x given y, maybe we just want x, regardless of the value of y. So is it possible that we can obtain it? So if we look at this perspective from the law of total probability. So let's assume that we have our probability space partition, and let's assume we partition with respect to y. So this is y1, y2, y3, y4, and there could be infinitely many subpartitions here. And let's assume that we want to represent this event x. Then the probability that x takes the value of little x can actually be represented as the sum across all values of y of probability of x comma y of xy. And here this is the joint probability mass function for x and y. So joint probability mass function for x and y. And by Bayes' rule, so by the Bayes' rule, then we can write this expression in the following way. So the probability mass function, or the marginal probability mass function for x, taking little value of x, can be represented as the sum across all values of y of the marginal probability mass function for y at value little y times the probability, the conditional one, x given y, of x given little y. It's very important that notice that this is going to be summed across all values of y, and we're still going to have an expression with x in it. So this is indeed a function of x, which makes sense with the notation on the left-hand side. So giving a marginal function for y and a conditional function for x given y from the law of total probability and Bayes' rule, we can obtain the probability mass function for x. Let's look at an example of how we would use this in practice. Let's suppose that x is a negative binomial random variable with parameters p and nu. And let's assume that this parameter nu is actually not a number, but a random variable, in particular, a geometric random variable with parameter q. So, what exactly do we want? So obviously, representing a probability mass function for nu is pretty straightforward, because its probability mass function, since it's a geometric one, is given by p nu, and let's assume its variable value is going to be represented by little m. This is going to be equal to 1 minus q to the m minus 1 times q. And since it's a geometric random variable, the domain is 1, 2, 3, 4, and so on. Now, one may try to do this same thing for the negative binomial random variable, but we don't know the value that nu takes because it is a random variable. It could be 1, 2, 3, 4, and so on. Obviously, if nu takes the value of 1, x is a geometric random variable, but if nu takes any values 2, 3, 4, then it is indeed its classical representation of a negative binomial random variable. So how would we represent that distribution? So it's obviously going to be a conditional distribution since it depends on the value of nu. So we're going to write it as x nu, and let's assume it takes values little x and little m. And since it's a negative binomial random variable, its PMF is going to be equal to x plus m minus 1, choose x, times 1 minus p to the power of x, p to the power of m. All right? So these are our PMFs, but one is a conditional PMF and one is just a classical PMF. So our question that we want to answer is the following. Can we obtain the marginal probability mass function for x without having to know the value of m? And all we need to know is the values of q and p in order to represent x. If so, then we can rewrite this conditional PMF as just a marginal PMF using the tricks that we've already learned up to this point. So how are we going to do this? So obviously the answer is going to be yes. So you may want to pause this video and see if you can do this on your own. So the marginal probability mass function for x is going to be equal to what? So we're going to sum up across all values of n. And since n is a domain of a geometric random variable, we're going to go from 1 to infinity, and we're going to be using the law of total probability to represent the probability that x takes the value little x. So from the law of total probability, we're going to have p nu of m times p x nu x given m. So this is just the law of total probability. Now I'm just going to quote these particular probability mass and conditional probability mass functions directly. So what are we going to have? So we're going to have the sum from n is equal to 1 to infinity of x plus n minus 1, choose m, and then we're going to have 1 minus p to the power of x, p to the power of m, 1 minus q to the m minus 1 times q. Now what I'm going to look at is everything that has n in it. So these things have n in it, and everything that does not have n in it, I can actually factor it out. So this 1 minus p to the power of x, and this q as well. I also want you to pay attention that these exponents are n and m minus 1, so I can actually break apart this pn into p to the m minus 1 times p, and then group together this pn minus 1 and this 1 minus q n minus 1 into the same power of n minus 1. So once I perform that decomposition, I'm going to have 1 minus p to the power of x, and then I'm going to have a p and a q factored out of my sum, and then I'm going to have the sum from n is equal to 1 to infinity of x plus n minus 1, choose x, times p times 1 minus q to the power of n minus 1. Right? And there's not much algebraically you can do with this unless you know a little bit about infinite series. So the first thing that I want you to pay attention to is this object, p times 1 minus q. Those are just two probabilities multiplied together. So I'm going to call this value of y, and I'm also going to note that this is between 0 and 1. I'm also going to re-index my sum n is equal to 1 by doing a quick substitution for n minus 1, and I'm going to call m to be equal to m minus 1. Obviously, when n is equal to 1, we're going to have m is equal to 0. So my probability mass function for x can now be represented as 1 minus p to the power of x times pq times the sum from m is equal to 0 to infinity of x plus m, choose x, and then we're going to have y to the power of m, where y belongs to the interval 0 to 1. Right? So now what we have here is practically a geometric series. In particular, it's a combinatorial geometric series. And one of the identities that you definitely should know about combinatorial geometric series is the following. In particular, the sum from n is equal to 0 to infinity of m choose x, where m ranges from 0 to infinity, of y to the power of m. This is actually equal to y to the power of x all over 1 minus y to the power of x plus 1. This is a very important identity. So notice that the only thing that's really missing is we're missing the x plus here, and the only thing that really changes is the numerator of that term. So once we use this beautiful identity, what we're going to have here is px of x is equal to 1 minus p to the x, pq, times 1 over 1 minus y to the power of x plus 1. So once we have that, then I can actually decompose this x plus 1 into an x and 1 term and combine those x exponent terms together. So once I have that, I'm going to have that the marginal probability mass function for x without n in it is going to be equal to 1 minus p over, and let's replace y with what we defined it to be. So 1 minus p times 1 minus q, and that's all raised to the power of x, times this constant pq all over 1 minus p, 1 minus q. Right? And this would be the marginal probability mass function for x, and notice that we do not need the value that nu takes, in particular m. Right? And this is a little bit more practical in terms of its uses for the applications of this negative binomial random variable. Now that we know how to deal with conditional probability mass functions, and similar for probability density functions, let's deal with conditional expected value. So let's quickly review what we mean by expected value in the discrete case. So the expected value of a discrete random variable x can be found by summing across all possible values of x times the associated probability mass function for x. So similarly, we're going to define the conditional expectation of x given a value of y, and this is going to be equal to, again, the sum across all possible values of x times the associated conditional probability mass function x given y of little x given little y. Okay, so keep in mind that this, since we're summing across all values of x, is going to be a function of the value y. Same thing as EX, y. Okay, so if that is the conditional expectation of y, let's assume again that we're giving the conditional probability mass function pxy, and obviously from this definition we can get the expected value of x given y, but can we just get the expected value of x even if we do not know the value of y that is taken by the random variable capital Y? So if we use the law of total probability again, then we have that the expected value of x is actually going to be equal to the sum across all values of y if we partition the x space with respect to y, and then we're going to have the probability of y and then times the expected value of x given y. And let's assume that y takes the value of little y. And that's how we can find the expectation for x if we know the probability mass function for x given y. From this definition, we can get EXY, and then we can use this to find EX without the little y given. Let's go back to our example where we had the negative binomial random variable x, and that random variable nu that was sort of needed for that parameter for our negative binomial distribution. Okay, so let's sort of go back to what we built there. So the probability of x given nu, of x given m, was equal to x plus m minus 1, given x, p to the power of x, 1 minus p to the p to the m, and then p nu was equal to 1 minus q to the m minus 1 times q. Now let's see if we can find the expected value of x, even though we were given the conditional function x given u. So using the already derived properties, we're going to have the expected value of x. Again, we're going to be summing across all values of m, which is obviously going to range from n is equal to 1 to infinity since it's a geometric random variable. And then we're going to have 1 minus q to the power of m minus 1 times q times the expected value of x given u is equal to m. Right? And keep in mind that this is for a negative binomial random variable. Right? Because that's what x is. So, using the definition for the negative binomial random variable, what are we going to have? So it's going to be, again, the sum from n is equal to 1 to infinity of 1 minus q, m minus 1 times q. And then the expected value for a negative binomial random variable is going to be equal to m times the associated probability parameter 1 minus p all over p squared. Okay? Now I'm going to factor out everything that does not have an n in it. So what does not have an n? So we have this 1 minus p, we have this q, and we have this p squared on the bottom. So once we factor those out, we're going to have q, 1 minus p, all over p squared, multiplied by the sum from n is equal to 1 to infinity of, what are we going to be left with? So we have that n there, and then we have this 1 minus q to the m minus 1. Okay? So what I want to do now is I want to let 1 minus q be equal to y. Obviously y belongs to the interval 0 to 1. And obviously if this is the case, 1 minus y will be equal to q. We're going to need that to replace a little bit later. So if I rewrite this, then I'm going to have the expected value of x will be equal to q times 1 minus p all over p squared times the sum from n is equal to 1 to infinity of n times y to the m minus 1. And if you notice, this is just a power rule for derivatives with respect to the variable y. So if we rewrite this in terms of differentiation, and then factor out that differentiation operator, what we have here is this is just the partial derivative with respect to y of the sum from n is equal to 1 to infinity of y to the power of n. Right? So that's actually really, really nice. And what we have here is a geometric series that starts at n is equal to 1, and we already know what that converges to. So this is going to be equal to q times 1 minus p over p squared times the partial derivative with respect to y of y over 1 minus y. Now we need to partially differentiate this quotient with respect to y, right? So obviously we need to use a quotient rule for derivatives here. So bottom derivative top minus top derivative bottom over bottom squared. And that's going to give us what? So we're going to have the expected value of x is equal to q times 1 minus p over p squared. Now for this derivative, a lot cancels out. In particular, we're just going to be left with 1 over 1 minus y squared. And we already know what 1 minus y is equal to. That's just going to be equal to q squared. So since that's equal to q squared, we have that q there and that q there, so a lot of the stuff cancels. And from here we have the expected value of this negative binomial will just be equal to 1 minus p all over q p squared. And notice that nowhere in this expression do we have n, right? So this would be the marginal expectation for the negative binomial random variable x, even though it originally depended on the value of n. Now that we have a basic understanding of conditional expectation and conditional probability theory, let's talk about some of the important properties of conditional expectations that you definitely should know. Now, a lot of these properties should look very familiar to you from the basic probability properties of expected value, but they do have a little bit more of a general notion associated to them, right? So we already know that the expected value of a constant is the constant itself, but you can have the expected value of a constant given a particular value of x. Even though somebody gives you a value of x, the constant doesn't really depend on it, so you still have that the expected value of a constant is still a constant even in the conditional case. And also, since the expected value is a linear operator, conditional expected value also will follow this typical linear operator case. That is, constants can factor out of expected values, and also expected values can distribute over addition, even if the variables x and y are not independent variables. Also, if an x variable, either it be continuous or discrete, is a non-negative random variable, then the expected value of x given a particular value of y is also going to be greater than or equal to 0. So that's actually pretty nice. You know, integrals also have that type of behavior as well. Also, if x and y are independent, then the expected value of x given y is equal to the expected value of x. That's a very familiar property to most people, but this last property is actually quite interesting, and it's the expected value of x given y is equal to the expected value of x. Some people will refer to this property as the law of total expectation. Some people also call it the law of iterated expectations. Some people also call this Adam's law, right? But I'll just refer to it as LTE, or the law of total expectation. And since this property might be new for some of you, especially if you've never worked with conditional expectations, let's actually go through a nice little proof of this little property. So let's prove property E. The proofs for the other ones are practically the same as usual. So what is the expected value of x given y? So let's actually figure out what the heck we're looking at here. So keep in mind that this is going to be a function of little y, right? So it's going to be a function of capital Y given little y. And obviously the expected value of y is going to be equal to some number, right? So let's figure out what that number is equivalent to. So by definition, the expected value of this random variable, or function of a random variable, is going to be equal to what? So this is going to be equal to the sum across all values of y of py of y times the expected value of x given y. So that's the definition of the expectation of that variable. Now what I want to do is I want to explore that expectation inside of this bracket. So when I do that, what I'm going to have the sum across all values of y, and then I'm going to have the sum across all values of x, and then I'm going to have x times p of x given y of x given little y, and we still have that p y term hanging out inside of our brackets. Now what I want to do is I want to slightly rearrange this. So since sums are commutative, I can interchange these sums quite nicely. So this is going to be equal to the sum across all values of x, and then I'm going to do the sum across all values of y, and then I'm going to have x times pxy, x given y times py of little y. Now since my interior sum is y, everything that only has x in it I can factor out. So I can pull out that x there. So this is just going to be equal to the sum across all values of x of x times the sum across all values of y. And then I'm going to have, let's do this as pyy times px given y of x given y. Now this term should look very familiar to you. That's just the product rule for probabilities. You know, the probability of A and B is equal to the probability of A times the probability of B, assuming A has already occurred. So we can write this as the sum across all values of x times the sum across all values of y times the probability that x is equal to little x and y is equal to little y. And notice here that we're summing across all values of y, and we have this x here. So if you look at this from the graphical perspective, what we're looking at, since we're summing across all values of y, for example, we have y1, y2, y3, and we're representing the probability of some event x here, right? So let's erase that circle. Let's do a different circle here in terms of color. So let's assume that that's x. So this is just a partition of x with respect to y. So if that's the case, then that's just the probability of x. So if that's the case, that means this is just the sum across all values of x times the probability of x, represented in terms of the intersection of x with y by the law of total probability. And keep in mind, this was the expected value of x given y. But what exactly is that expression? Well, that's just the definition of the expected value of x. So therefore, the expected value of x given y is precisely equal to the expected value of x. Right? And that's the law of total expectation, a very, very useful property, and the proof associated to it. Although the previous set of conditional expectation identities are very useful, they can easily be generalized to functional representations of conditional expectation. For example, instead of x, you can have a function of that random variable x. Instead of y, you can have a function of that random variable y. So, for example, the first few theorems here, the expected value of f of x times y given a value of x, where the f of x value can practically be factored out, practically still holds here as long as the thing you're factoring out is with respect to the variable that the condition is set with respect to. Now, a couple very subtle differences is that when it's inside of the bracket of the expectation with respect to x, when it factors out, it turns into f evaluated at the value that capital X actually takes, because this capital X is when capital X takes value little x. So when you factor f of x out, it turns into f of little x from f of capital X, right? So that's a very important subtle thing that some people forget to take with respect to. Because keep in mind, expected value should be a number, not a variable or a function of a random variable. Similarly speaking, if you have the expected value of the product of two functions, f of random variable x times g times random variable y, with respect to y, g of y can be factored out, but it turns into g of the value that capital Y takes times the expected value of everything that's sort of left out. Similarly, again, expectation is a linear operator, so it can distribute over addition, and constants can factor out. So you have the sum or linear combination of conditional expectations of f and g with respect to y. Just like before, we have a non-negativity condition. That is, if f of x is greater than or equal to 0 for all x in the domain of f, then the conditional expectation of f with respect to y will also be greater than or equal to 0. And if x and y are independent, then the expectation of f given the value of y, again, f of x doesn't really care about the value of y since they're independent, that's just going to be equal to the expected value of f of x. The total law of expectation also has a general one, which I can present here as well. And keep in mind that was the expectation of x given y, but now we can say the expectation of f of x given y, and this of course generalizes to the expectation of just f of x. So that would be the generalized law of total expectation. Some people, again, will call this Adam's law, or the law of iterated expectations. And another very important theorem is that if you have an expectation of a function of two variables, that's not necessarily decomposed. So for example, h of capital X, capital Y, given some value of y, this is actually equal to the expectation of h evaluated at random variable x and the value little y, assuming that capital Y takes the value little y, right? So the only difference is that inside the expectation, you can turn y into little y as long as the variable you're working under is the variable that you're shifting, right? And obviously a generalization of these can also be taken. So I guess a generalization of Adam's law can be viewed as the following. If you have the expectation of y given g of x, and let's assume that that exterior expectation is also conditional with respect to the composition of f with g of x, this is actually just equal to, so some subtle things there. So this is a random variable. That's the condition for that expectation, but this interior has variable, and that's the condition for that expectation, right? So a nested set of conditions. This is actually equivalent to just the expected value of the variable that the interior expectation is with respect to, assuming that the condition is f of g of capital X, right? So a lot of simplifications can take place there. Now, the proof of these practically follow the same exact general approach as we did before, but there's a couple things that I want to mention, especially in terms of what these things can be used for. So if we write, for example, y to be equal to y, I don't think anybody can disagree with that, and add and subtract the same exact thing. For example, I can add and subtract ey condition x plus y minus ey condition x. Now, why do I want to write it like this? So I want to look at this term and this term here. So this is the expected value of y given a particular value of x. So one can say, okay, well, what value will y take on average? Well, the expected value of y would be that answer. But maybe if you give a little bit of information about x, maybe that can help you actually estimate the value of y, especially if y and x are dependent random variables. So there is an application that we've already used where x and y are dependent random variables, and that's regression, linear regression in particular. So we can actually view this as beta 1x plus beta 0. So if beta 1 and beta 0 are just numbers, and I give you a particular value of x, that can actually help us predict the value of y. And the rest of this would actually be a residual. It is the value you're trying to predict minus the thing you're trying to predict it with. That would be precisely a residual. So you can actually view conditional expectation from the perspective of estimation theory, right? In particular, the expected value of y given x can actually be used to predict the value of y, and you should be able to show that that actual expectation of y given x is actually a very good predictor for the value of y. Right? So the expected value of y can predict the value of y, but keep in mind the expected value of y given x is a number that depends on x. It's not just y, which can take some number. Right? So just keep those things in mind. Now, before I say goodbye today, I just want to briefly define conditional variance, because we talked about conditional probability theory, conditional expectation. What about conditional variance? So the conditional variance is going to be defined in a similar way of y given x is given by the following expression. So the variance of y given x, is equal to the expected value, so this is the classical approach, of y minus the expected value of y given x squared. And obviously this needs to be a conditional expectation given x. Right, so that's the expected value. So the variance of a variable y, keep in mind, so the variance of y will actually equal to the expected value of y minus the expected value of x squared. That's how we define the variance of a random variable y. That should be the expected value of y, not the expected value of x. And this would be how we're going to define the conditional variance. Now, a couple very important theorems that you definitely should know if you plan to work with conditional variance are the following things. So the first thing that you definitely should know when it comes to conditional variance are the following. So the variance of y given x does have, once you expand this little expression, the second moment minus the mean squared equivalent version. So the expected value of y squared given x minus the expected value of y given x to quantity squared. So most people who don't like the original definition of the variance of a random variable usually work with this variation, as it sometimes is a little bit more easier because calculating the second moment of a random variable is usually not that bad, where the original definition is usually a lot more computationally expensive. Another very important thing is the following. That is, the variance of y can actually be represented as a switched version of expected value and variance. In particular, the expected value of the variance of y given x plus the variance of the expected value of y given x. Right, so notice that I've switched the order of expected value and variance in each of these things, but the independent variable is still the same. Okay? So this is actually quite interesting. Some people will refer to this as Eve's law. Eve's law. And this has a lot of applications in the realm of statistical testing across multiple groups. Because some people, especially when you start talking about ANOVAs, this looks like the total variation of y. And this is sometimes going to be referred to as the weighted average of the variation within the groups that you're studying. So for example, if you're trying to see if there's a significant difference across these groups, for example, if you're doing the mean of this group, mean of that group, mean of that group, mean of that group, is there a significant difference between the means across all 5 groups? Then obviously you need to figure out, okay, well, is there a lot of variation within each of these groups? So that's practically what the variation of y given x is. So for example, I give you x1, x2, x3, x4, and x5, and these are all y values. Is there a significant difference between the heights of different age groups? Yes or no? And the expected value practically is a weighted average of those variation parameters. And then the variation over here, that's going to be the variation between the groups. So for example, is there a significant difference between the average of x1 and x2, x2 and x3, x3 and x4, x4 and x5, and all other permutation pairwisely that you could conduct? So this theorem, I guess you could say, is used to do a lot of those analysis of variance type of tests, which we'll definitely discuss if you haven't already. And another theorem that ties actually really well with those type of tests is that the expectation of the variance of y given x, that is the variation within the groups, the weighted average of all of them, is actually always less than or equal to the total variation across all values across all groups. Right, so those are definitely some things that you definitely should know if you want to explore conditional variance. But those are some of the theorems that you should know in terms of conditional expectation and conditional probability that we'll definitely use in the near future. Hope you enjoyed this video, and I'll see you in the next one. Take care.